Okay, so today we have the pleasure of having Brando, who's my PhD advisor, so extra special today, and who will tell us about positivity and massive higher spins.
Okay.
Please take it away.
Okay, so let me, thank you for the invitation. It's a real pleasure to be here in the Sierra Leone, my first time. And I will tell you about something which is really an ongoing project that was started 2 months ago in collaboration with Alex Pomerò, the student Francesco Sciotti, my student Marcello Romano. And I want to stress that this is really like preliminary. I mean, many of the results have been worked out maybe last week or the week before. But since I'm excited about it, I wanted to report it anyway. And it's about the following question, okay, that arise from the fact that when you build IPhT theories, often basically never consider a massive high spin at the bottom of the spectrum in isolation with a parametric gap to other states in the theory. So always they come, for example, in strongly coupled theory, if you have a massive spin, high spin at the bottom of the spectrum, this scale it comes with other excitation, a parametrically the same scale. Or if it's parametrically separated, is a low spin. For example, you can arrange as spin 1/2 or spin 0, spin 1. Or, but never arrange a situation where you have a massive high spin separated parametrically by something else. So we wanted to understand whether this is a genetic feature and what is the source of this is generic. So can you engineer a situation where you have a massive high spin at the bottom of the spectrum, nothing else up to some higher scale? And the short answer to this question that I'm going to argue is no, that is not possible. That's why it's never realized. And I want to explain why, what are the ingredients that bring, that forbids this situation. And it's important to stress some of the assumptions that we're going to make. So first of all, I'm going to call little m the mass of the light particle, one sitting here. I'm going to consider high spin, meaning bigger than 3/2. The theory here can be arbitrarily strongly coupled. But I will assume that the theory here, the energy around its mass is actually weakly coupled, such I'll be able to use the IPhT theories in this range. And we'll see other assumptions that will come in a second. And let me state the reason why this is possible, then we will work out through the details. So the reason at the end of the day is because of causality. Okay, so the fact is that if you have a gap between the mass of other states and the mass of the particle you are interested in, you can dial your system, you can probe the system at energy much above this mass and below the other states. In that regime, your state has a lot of polarization to grow with energies, okay, in terms of fields. That fields can carry a lot of derivatives. And so the amplitude can be small, but it grows quickly with energy, okay? Even maybe remaining small within the IPhT theory. But that is going to be forbidden by causality. The highest power here within the IPhT theory can be 4 at most. They can have higher powers, of course, but can be sub-leading. They never dominate over the if before being. And also, I want to stress this has nothing to do with the. It's nothing to do with the perturbative irregularity. All the bounds so are going to be expressed in terms of like projective or ratios of couplings or some homogeneous inequalities like this. And so it doesn't matter whether here you have a 10 to minus 15 in front. So the amplitude will never hit the unitarity bound. It really is the energy growth that will set the constraints. And this goes, the main reason goes back to this beautiful paper by Adams, Ahmed, Rattazzi, Dubosky, and Nicolis, where they show that if you start with the free theory and you perturb it arbitrarily small, but with an operator which has the wrong sign, you can build configurations a background configuration where your perturbation propagates superluminally, and is enough if you have a particle that propagates superluminally even a little bit, you can do it so for a long time, so within the IPhT for long distance and long time, they accumulate a visible time advance and build time machines. So this is really not about size of the coupling, it's really about structural property related to causality. And in a sense, another way to see it is that a free theory is on the verge of inconsistency. So if free massless theory propagates superluminally, you can expect a perturbation, like a wrong perturbation, one that violates one Wilson inequality, will push you outside the line cone. So it's a very delicate theory, the free theory. And I will show that, of course, there could be fix to this. And the fix is going to be by changing the theory. Okay, you're going to change the degrees of freedom that you see at the bottom of the spectrum. And in particular, we will see that if you insist with a finite number of Eigen spins, this will lead to the presence of gravity necessarily in order to satisfy the causality constraints. And the story will be interesting. There will be an integral connection with this one-point problem. And in fact, this set of questions I discussed is part of a bigger program, bigger picture that we are Lorentz observer living here, trying to parameterize the IPhT theory in terms of tau as a eigendimensional operator. But of course, a generic point in the space of this IPhT theory doesn't come from any consistent parent theory. It's not the endpoint of energy evolution of a macroscopic theory. So it would be nice to be able to tell apart theory that lives here in the small plot from theory that lives here that come from some RG evolved theory for short distance to long distance. And essentially this means that we should be able to track down some, at least generic and general features along the RG evolution. And the tool I will use to track these properties are dispersion relations and the IPhT theories. And this goes on under the name of positivity bounds because it's a lot of inequalities. So here's where causality provides precisely this link. And causality means that you control the analytic structure of your scattering amplitudes, in this case, 2 scattering amplitudes. In this case, a fixed momentum transfer in the center, in the analytic, in the center of mass squared, center of mass energy squared. And that's what it provides the link between the UV and IR along the RG flow. So if you work here, you're interested in these regions of small energies, you do a contour of some amplitude in the infrared. So that's what you calculate in the IPhT theory at the endpoint of your RG evolution. Because analyticity comes from causality, you can define this contour to run along the discontinuity of your theory. And this extends all the way to infinity. So we know about properties of the UV that you cannot calculate because you don't know the UV, you access only the IPhT theory. But you know general property of discontinuity nevertheless. So this is a parametric example that shows this. So you consider a scattering amplitude for a scalar, for example, a zero momentum transfer. Just identical scalars, you get is a polynomial in the IPhT theory of energy. And you can access each Wilson coefficient here by doing a contour that I'm going to call arc, referring to this contour integration over your amplitude divided by a suitable polynomial, in this case a monomial, the peak, depending the n I choose here, we select one Wilson coefficient at a time. So this arc has a double representation, has a representation in the infrared, calculated this way. It gives me, in this simple example, it gives me one Wilson coefficient at a time. But it also has a UV representation, where it's calculated this way, as an integral with discontinuity. And I'm not able to do this calculation. Nevertheless, these two are equal because of analyticity. Therefore, I can immediately conclude that this Cn is positive, because this is the integral over discontinuity, which is positive because of the optical theory. In fact, I can see more, because I can see that this is a positive, yet unknown measure, integrated over the variable 1 over s. So I can interpret the Wilson coefficient as moment of opposite distributions. And moments are not generally set of, it's not just random set of numbers, but they satisfy various constraints, and this will therefore imply constraints on the structure of which the coefficient is different. So let me give you a explicit realization of this in this simple toy model. So as I said, your arcs, this contour that you infrared, pick one Wilson coefficient at a time in units of the scale of the gap to the heavy states. And capital M is the mass of the heavy states. The sets, the niche, where the discontinuity starts. And then, because analyticity is, as I was showing before, this is nothing but a moment of an unknown positive distribution. So clearly these are positive, but more can be said, because I can test any positive function by integrating against positive functions. In this case, for example, in the interval 0, 1, I can integrate against this function here. X to the n gives me the one of these Wilson coefficient Cn. X to the xn plus 2 gives me the following one. I get that this is positive, therefore they are monotonically decreasing, for example. So that's one trivial constraint. So you cannot just give a random set of numbers, they have to go monotonically down, starting from the first from which this dispersion relation was converged, which happens to be this one. So that's why that's the energy to the fourth that was alluding at the very beginning comes from this. The first moment that gives you a dispersion relation is going to be the one the largest of all. So it's never dominated by the other ones. Instead, the ones which are below that are going to be free. And you can do more. Okay, so you can do more. For example, you can integrate your unknown discontinuity against some square, which is positive for random coefficients. And that means that this matrix of Wilson coefficients must be positive definite, and therefore C2 times C6 minus C4 squared is also positive. And so if you plot it, the space of Wilson coefficient have to live actually, in this case, projected on two of them, must live in this window, in this wind-like region. And you see that's completely non-generic. So at a point, I could have imagined a situation where I have a symmetry that kills this guy, but not the next one. It would have put me a point here that symmetry would be consistent with causality and unitarity I will be using so far. So the structure of effective fifth degree coefficients that you get in the infrared remembers parts of the formation of the UV. In particular, in this case, remembers that the UV theory was causal and UT. And that G4 doesn't destroy completely these formations. And this, of course, this example that I discussed was in a very simple model. The momentum transfer, but it works for all Wilson coefficients. For example, a finite T has been generalized in various nice papers. For example, the coefficient is missing here. The first one would be STU, where it's a Van der Stam. And this C3 can never be larger than C2. It can never dominate the C3, this STU can never dominate, for example, over C2. Again, into the fourth is the first one that cannot be, is necessarily there and cannot be dominated by terms appearing later in the energy expansion. So why I'm saying this? Because the lesson, okay, as I said, so everything, so you get the Wilson coefficient constraint to be in certain regions, double-sided bounds. E to the fourth term must be unsuppressed right to the other. But the interesting part for me of this story here, at least, is that this means that if this carries through Huygens spins, this is going to pose a problem to this theory because Huygens spin, despite that it actually will grow a lot with energy. But here instead, E to the fourth should be leading, whereas if you have, for example, write this one to the fourth power, in the sped it will grow like in the naive case, in the sped 4 to the spin, E to the 4 times the spin, which of course could be much larger than E to the 4. So it seems to be a tension. This carries through. Seems to be a tension between having an effective theory with a high spin at the bottom and causality and unitarity from the left side. So I want to study whether this is the case. That's what we set up. Is this expectation valid? When it holds, can I fix it? What does it take? Okay, these are the kind of questions. I'm interested in looking at the boundary case. 3/2 is going to be a nice case because in the generic, so if I don't add new degrees of freedom, the spin 3/2 will fail the causality condition. It will not be possible to have it at the bottom of the spectrum alone. However, there's going to be a fix for the spin 3/2, which is going to be adding gravity. Of course, if I add, we know that, for example, I can write supergravity theory, there's no problem having a spin 3/2 particle lie at the bottom of the spectrum, but that requires gravity. There's another state around, which is the gravity. So what it comes out, that would be the only option. There's no other way to make it so. That's because it comes from causality. So this is an interesting playground for this story. So let me go through the spin 3/2 as a case of study. So this is the assumption, okay, I'm going to make. I'm assuming the lowest number of degrees of freedom in the infrared, in this case 4, 2 elicited 3/2 and 2 elicited 1/2, or I might run a spin 3/2, and then some desert up to some scale M, and then just some new states appearing here. And imagine whether, for a reason by contradiction, I imagine that this M is much larger, the gap is much larger than the mass of the particle. So I'm going to put myself at edges which are much above this one, much below this one, which I can use the statistical theory. And in that regime, the leading operator controlling the effective theory are the lowest dimensional ones are these three. It doesn't matter too much, just there are 3 of them. And they map to 3 coefficients in the amplitudes. This one, this one, and this one. Some linear combinations. In this case, I'm looking at the amplitude for scattering, just spin 3/2. And I'm looking at the longitudinal polarization 1/2, are those which grows fastest with energy. So in the limit where the edge is much larger than the mass, basically I recover a sort of massless particle for the longitudinal. So I pull out the little group photon here in that limit. I get what I would expect. I would expect that the polarizations, the longitudinal goes like e to the over m to the 3/2. So for 4 of them, I get e to the 6. Indeed, this operator turned on, this goes like e squared, e to the 4th. Indeed, it turns off this one, and this one, returned by this operator. This one is subleading. It contains the subleading correction to this limit. So it's one power as a power insertion of a mass. So it's proportional to the mass. This one is suppressed relative to this. Okay? The ratio, this one over this one is basically E over M. And you see there's a tension here because E squared times E squared is E to the 4th. I was insisting in the scalar example that E to the 4th cannot be suppressed, it should be leading to the next. So instead, this effective theory seems to suggest that's not possible. So is that there tension with positivity? So that's the thing I want to establish whether it's the case and whether under what condition I can get around. So in order to carry the story, I mean to compare to the simple scalar case, there is a little bit of some technical tools that you have to develop to see the constraints from causality in a clean way, and which is sort of the using-matic version of the usual fixed T dispersion relation. This is a fixed, it's going to be a fixed TU over S dispersion relation. So you fixed not just one Mandelstam and dispersed in the other, but you fix these combinations of Mandelstam and dispersed in the supermass energy square. This is because this, when you scatter this configuration of elasticity, of course, you can exchange 1 and 2 here. That means this besides the little group photon from this function here is TU symmetric. So it's very convenient to keep this fixed and expand it this one. This is a sort of a small momentum transfer. This becomes, and call this combination P. It becomes pretty much equivalent to momentum transfer, but it's a sort of generalization that's convenient for particles which are not identical. And the dynamic structure changes a little bit relative to the usual case, because this change of variable introduces new singularities, and you have to be careful whether you're crossing new branch cut you introduce this way or not. And however, that change of variable, you know what you're doing, just explicitly you know the discontinuity you're introducing. So you can check what's happening, whether you cross this extra discontinuity you're adding, or whether you're not crossing it. The difference amounts just to exchange T and U. So for example, if I have a discontinuity in S channel, I want to go to discontinuity in the U channel. Typically, if I have a mass gap, there's no problem going through a certain path and reach the branch cut. If I go through now to this extra singularity, in principle, I would exchange, flip the sign of the square root here. But that amounts simply to exchange T and U, since the theory is TU symmetric, actually doesn't do any harm. And moreover, respects also the range of scaling, meaning that in my dispersive argument, when I deform the contour, I can still drop the behavior of the arc by contour at infinity. I still get contribution only from the discontinuity on the physical branches. So it seems okay. And therefore, I can run the usual argument. Now I fixed this generalization of momentum transfer. And I can relate my infrared physics to UV physics doing contour in the central mass energy square. So let's see what do we get. So we get yet a further generalization of the example I presented at the beginning. We get that the Wilson coefficients or linear combination Wilson coefficients are not just moment of a positive distribution, they are 2D moment problems. So the measure, so here you get an example. So I get, I integrate my amplitude by a certain choice of n here. I pick some linear combination with some coefficient that depend on the variable I'm keeping fixed. And I get, so let me explain the notation, I get some, on the right-hand side, I get some moments. But now my measure support both in the energy square and in a discrete set of points, which are the angular momentum. Okay? Because basically it's having a final momentum transfer, so the kinematic, the angular dependence of the discontinuity is really known by expanding partial waves. And so this could be a little bit the story, but not too much. Okay, so at the end of the day, it's still true that Wilson coefficients are nothing but particular linear combinations of moments, in this case 2D moment problems. This function PL is nothing but the Legendre polynomial that we get expanding in some channel, in this case the VCT minus minus going to minus minus, and this one you get a Jacobi polynomial by getting this from a linearity in the partial Wilson function. So again, there's a map between Wilson coefficients and moments of positive distribution. And this is true for any value of the momentum transfer, this generalized momentum transfer in keeping fixed. So I can match the behavior on both sides of the P dependent and extract each Wilson coefficient separately. Okay? So for example, the lowest Wilson coefficient is just a sum, or in this case, minus this Wilson coefficient is the sum of the lowest moment. The next one is a moment only in the energies, and the next one is a moment both in the energies and in the angular particular combinations. So this is the UV prediction. And the UV, or if you want, is a way to calculate. If I knew the UV, this would be an alternative way to do the matching that the IPHT coefficient. If you knew the UV, you can do the matching this way. For example, this coefficient is given by doing this integral. Okay. But we don't know the UV, so we cannot do the matching. Nevertheless, we can get constraints on relation between these Wilson coefficients. And it's not difficult to see, for example, the first one would be this one. It's not difficult to see because minus C10 is just the first moment plus the other moment. If I take the norm of this, so it's bounded by replacing this with a plus, and 1 over S here is smaller than 1 over M. Because because the S here runs from m squared to infinity. So 1 over s is actually smaller than m. So I can bound it by m, which is precisely what is written here. C20 multiplied by m squared. So I get m squared over s, m squared over u, which is less than 1. But this one was less than this because I put an absolute value, so I get precisely this bound. So very simple, very simple. So without doing any effort, I know that the next expansion in energy is actually bounded by the previous one. Okay? This causality creates the link, and unitarity is constraints on the sides. Okay? Now the other one, this one is a bit harder to get what the constraint is, but it's clear that it should be a bound, because if this was the connection coming from unitarity and analyticity, you see that on the left-hand side, you have a function of p, so a linear polynomial, with slope given by the Wilson coefficient C21. So it's some line. The slope, as you vary this Wilson coefficient, it will change the slope. On the right-hand side, however, you have the moment of polynomial, which is bounded. So the polynomial bounded by 1 and -1. So in the range where I have my analytic structure holding, both these and these are bounded above and below. That means that this slope here can never be too high, otherwise within the range of validity of this dispersion, it would exceed the bound provided by this quantity, the upper bound or the lower bound provided by this quantity. So it clearly must be an upper bound on the slope. That's precisely what you get by matching, by saturating this upper and lower bound, you get precisely the C21 times m squared over C10 is bounded above and below. You notice these are order 1 number. Okay? 2, 6, 1. So in particular, they are in complete contradiction with the expectation that C10 was suppressed by m squared relative to C20. And that's precisely the source of the problem. Okay? So causality implicitivities will tell you that this is impossible to achieve. And this that we see the contradiction, we assume that it had this effectivity. If you had that, this would be the hierarchy that you get in the ratio. So there's a clear contradiction. So this was working in the parametric terms. Saying there is a parametric separation between capital M, the mass of new states, and little m, the mass of the particle I want to keep at the bottom of the spectrum. I was working by contradiction, parametric, taking a very large separation, taking E very large, working with masses in the masses limit, and finding contradiction. Can we make it more quantitative? When this contradiction materializes? How big M quantitatively can be capital M relative to little m? How large can I get? And this is something that to answer this question, we use an approximate method that we developed a couple of years ago with Julia. And it's a bit complicated in the sense because now if you want to work, if you want to keep track of final mass effects, there are two sources, complications of this idealized parametric separation limit that was taken. One comes from your kernel and your dispersion argument somewhat different, so you keep track of that. And moreover, when you cross, so the discontinuity is positive in the physical region, and it's mapped. There's another discontinuity here, which is the physical electron mass square, which is mapped to the physical new channel by a crossing matrix which depends itself on the kinematics for massive particles. So it goes under the integral. So, and moreover, this crossing matrix makes all the listings. So the discontinuity is not just a positive number, it's a positive definite matrix, but there are a lot of negative entries. Moreover, this depends on the kinematics that you're integrating over. So tracking the details of positivity seems complicated. But what we realized is that every time you do transition from one helicity to another by crossing, more than what you would get in the massless limit, you pay a suppression. And this matrix that controls so there's a kinematic suppression, and multiplied by a matrix that controls the transition. And this matrix is bounded by the spin of the particle you're scattering. And moreover, the prefactor here you're integrating, the discontinuity, is also bounded because of unitarity to the elastic configuration. The elastic configuration you can recast directly in terms of the arcs that you're calculating the different. So everything, the error that you're doing relative to the idealized case, to the parametric separation between the gap and the mass of the particle, is completely under control.
What matrix normally?
So this is I'm bounding each coefficient. Each entry is bounded by this amount. And moreover, each transition costs you this amount. So if you have this little m is much more than Cat9, it's going to give an F for the suppression. So this allows you to control completely the error. Okay, so you can bound the error. And what you get is that these arcs, like now calculated at a final momentum transfer for various statistic configurations, are less than something now depends on that. Before where it was bounded by, so for example, for limit B1 or for mass value 1, and so on. Now you can bound it keeping track of the mass dependence. And also, for example, the arc or the Wilson coefficient, this will pick Wilson coefficient with the higher growth in energy. Before it was times m squared over the Wilson coefficient of lower energy will be bounded by 1. Now you see that little m show up here and there. You can track exactly the dependence. And you can ask when these are violated, assuming there's an hierarchy here, how large can this hierarchy be given that this quantity, these arcs, these integrated amplitudes are calculable within the FET theory. So that's the assumption. I assume I have a FET theory. Within the FET theory, I do calculate this, and then I try now to push the gap further until I violate this. And that's the largest gap I can grant it to my FET theory. So this is what we've done here. So these are the lowest dimensional operators. And if you assume in this plot, for example, I'm taking the mass, the gap to the light state to be a factor of 30. Take it. Massive spin 3/2 certain mass, and then next state 30 times heavier. I get 3 conditions from these, or 3 such conditions. They give me, they depend on the Wilson coefficient, depend on C1, C2, C3. They give me some line in the ratios of those couplings. There are ratios because I'm taking ratios of these arcs. So you have 3 couplings that depend only on 2 ratios. So you can plot it in a plane. You get 3 conditions. So each condition will give you a line in this plane, and 3 lines don't meet numerically to a point. So when the hierarchy is too large, there is no solution. There is no choice of those Wilson coefficient that will satisfy the constraint. Now you start lowering your requirement. You say, okay, take my gap to be closer to the mass of the particle. I lower it. Basically, this blows up this line a little bit, and eventually an intersection shows up. And this happens to be around 8. Okay? So there's no parametric, indeed, there is no parametric separation between the mass of the spin 3/2 and the mass of the new states in order to be compatible with causality. And so that's basically how the story goes for the simplest case. And the lesson is the following. So what I was saying at the beginning. So the massive spin 3/2 isolated, so with a gap in new states, is inconsistent. Okay? You really need to bring the other states, you need to, at least some other states has to come down with it in order to be to pass the constraints. It really comes from the energy growth on the amplitude, and it has nothing to do with the size of the couplings. And of course, that the analysis I've done was for spin 3/2, but it's clear that the same problem perceived in high spin. In fact, it becomes kind of even larger, even bigger problem, because there are even more polarization that go even faster than that. And this is precisely what we checked 2 years ago with Julia. and Sara and Francesco, we check just the case of massive spin 2 alone at the bottom of the spectrum, providing like a candidate for a massive gravity theory, and just same story. You get three conditions on a plane of the two parameters of the theory. They don't intersect, and the intersection shows up. This I'm plotting the intersection as a function of the gap relative to the mass of the massive gravity. And you see that actually a factor of 30 at most. If the gap of new states is larger than 28, there is no solution. So that means that there is no massive gravity theory unless you have new states parametric at the same mass of the gravity. This, of course, is a disaster for massive gravity, because mass of the graviton is tiny, and we haven't seen any of the other states. There is no scale in the universe where you can use massive gravity. So, of course, as I was saying, spin 3.5 is interesting because we know there must be a fix. But we know concrete, Lagrangian theory, you write down, it's okay, supergravity. So, is supergravity special? So, what's it special? What is it special about it? Or can deformations exist? Can I do something else? So, this is the next question I want to ask in this case, spin 3.5. Plus something else. That's the only fix, no? So I said, if nothing else, this is a gap, no solution. So I have to change the IPhT. I need to bring down new degrees of freedom.
Are there examples of UV completions with like starting from 3.5 and then you have like all the other states and you see they're not very separated without gravity?
Well, yeah. So if you take QCD with the one flavor, the lowest mode is going to be a spin 3.5.
No, it's not that, but you also have the eta prime.
Okay. The prime is even lighter. Yeah. It's true. It wouldn't be at the bottom. Yeah, it's true.
They want something.
With the baryonic set.
That's a good start.
Yeah. But you see, I think you can engineer a strongly coupled theory where at the bottom of the spectrum you get 3.5 and parametric is something else, which is yeah, you're right. Of course, there are also or the is the eta prime in the case that you want.
So can you say anything about massless spin 3.5 from this viewpoint?
Yeah, I'm going to get the masses. Okay.
Massless 3.5.
Well, so in a sense, what I'm going to show is that we know that when you take purely massless 3.5, it has 2 degrees of freedom. So here I'm talking about 4 degrees of freedom, and the problematic ones are the extra ones. Okay, but what is nice is that when I will see in a second, when you add gravity, now you're allowed to take this parametric separation. So you would expect that the limit of very light massless gravitino should be okay. So that means that the extra degrees of freedom probably need to fit in a Higgs mechanism. Okay. I will not be able to show that you need an Higgs mechanism, but yeah, it becomes natural if you don't have. Basically, if you can take this gap, arbitrarily large, you would expect that's okay to take even to masses. Because the source of the problem was the longitudinal, and if the longitudinal are no longer a problem, means that it must be a Higgs mechanism behind.
But not restricting masses gives them some old results.
There are issues.
No, but no, of course, the massless constraints just from the transverse, that's trivial. Yeah. The soft emission. But those don't buy you anything here because I can give it a tiny mass, then I no longer have the soft limit. Well, yeah, that's the easy case. Okay, strictly massless without gravity, that's inconsistent because there is the soft limits.
First, I was asking from this point of view, if it's something new to say.
No. I think no. So I haven't thought about it because I thought, since I knew it was already excluded, but yeah, I'm not sure. But I would say there's probably nothing new, but I can check. Yes. Yeah, because you see, So if you don't have anything else, you try to write, let's say, a Lagrange activity for a master split in half, gauging variant, you build some high derivative operator, you form like a sort of a Riemann version for the split in half. But I think it wouldn't grow crazily with energy. It would be less than equal. Probably wouldn't bound it. Wouldn't be bounded by that. If you go through even high spin, probably yes. If you go, I don't know, spin 5 exactly mass, probably you can bound it. Yeah, 3 I think probably.
So the transfer degrees of freedom, they don't grow like S squared.
I would say probably the 3 is probably the borderline case, go like equal force. Yeah, I think so. Yeah, exactly. In fact, yeah, it must be this way. It must be so because in supergravity is an effective theory. I can definitely add the eigenderivative term for the transverse. They will be fine. And I know the minimum one doesn't make it grow, so it will be the leading. Yeah, 3 mass is not fine. So let me come back here to the massive case. So let's try to fix it by adding only low spin states. So a vector is not going to do anything. I cannot fix anything because I was working in Majorana with the lowest number of degrees of freedom. So this is a neutral particle, it will not couple to it. The scalar does have a 3-point function. So I can imagine that if with this, so I suppress the contact where I'm working, that were giving me the energy growth. And I start and assume that playing with this one, I can indeed achieve that e to the 4th will be leading. However, it turns out that with the scalar, it comes to be with a negative coefficient, always. It's a square with a minus sign in front. So it's actually, I'm not going to show you, but it's not going to work. So therefore, the only other option is to add a graph. Let's see what is Basel. So now you have an extra handle here. You have a new operator you can add, which is a coupling to the energy momentum tensor. And of course, if you have a theory which has nothing to do with gravity, you just don't know gravity, it's not going to change the consistency of your theory. If you have a QCD is consistent regardless whether gravity is there or not. Yeah, that's like that. So the only way to suppress the e to the 6th is when you make this coupling here gravitational in size. Now in that case, then you can achieve a cancellation. You make this gravitational in size. So if now everything is gravitational in size, this term can cancel. Indeed, we find the cancellation possible. Okay? And moreover, when you achieve the cancellation, so you reduce this, now they can cancel against this contribution. So your theory is really gravitational, or the overall set of couplings set by Planck. And once you achieve the cancellation, the e to the 4th term is indeed positive. It's the sum of this term, squared, and t here is a negative momentum transfer, which is negative for the special relation. Oh, this is also positive. So it's a sum of positive terms. So it's okay. So this satisfies all the constraints. And moreover, now you can decouple gravity. So once you made the contact time gravitational, now you can take a double limit. So after you do this tuning, this cancellation between these two different effects, now you can send M' to infinity while keeping by setting the mass to 0. So you're approaching the very light gravitino case by making its coupling to the transfer more smaller and smaller. So the longitudinal will survive. This is going to come from the longitudinal by scattering longitudinal modes. Here, this will survive with something finite, and you will discover the theory of Gurstin, and which indeed comes with a square. Okay? So everything fits, and moreover, you learn, for example, you learn the Susy relation, the relation between the mass of the gravitino and the M Planck square is equal to the Susy decay constant. It's completely fit with the 3 factoring. So you don't need to open any Susy textbook. This is just causality using for free. So it had to be done.
But this is exactly Higgs angle. So you were saying before that's not obvious that it comes from Higgs angle.
Well, you see, this is it comes from causality. Higgs must be is compatible with causality. So that's where it comes from. So yeah. So Higgsing must provide this. So, I mean, Higgsing, of course, I'm scanning the longitudinal, so the longitudinal comes from a Higgs. It comes from the, I don't know, the Rafferty model. It will come from the superpart or some scalar. They are eaten here by the gravitino. So they are there. They are to be arranged exactly to satisfy this. So I don't need to write down any specific model. This might always be the case. Okay, this is also, let me open a parenthesis since we get the Agostini about, so the fatty of Agostino, since I can take this limit, now I can also, with the same technique, I can study the geometry, how the Agostino, what is the most general fatty theory of Agostino I can possibly have. And what we get is the following. So here I'm plotting the ratios of the couplings. And here, see this tilde here is a C20 over C210. And the positive bounds tell you that you have to live in this finite, so it's like you see as before, some double-sided bound, you have to live in some finite region of space, which is characterized by some corners here. Since this is a convex space, if you know the boundaries, you know all of it. And you can recognize, you can reconstruct the amplitudes that produce this point in the Wilson coefficient. These are Wilson coefficient which has 0 C21, but has C20 and C1, 0, 1. So it's this particular ratio Wilson coefficient. This one is another ratio, and so on. Each point here is a particular ratio Wilson coefficient. And at the corners, you can extract what the amplitude looks like. So what UV completion produced then Wilson coefficient. And you see very simple theories, these two corners here. This is just integrating a scalar in S channel in this process. And this one your exchange has been one in the cross diagram. And this corresponds to Rafferty, this one to Radiolopoulos models. And everything that you see here in the convex hull here is just a linear combination of the two. And just is what you would expect for an ordinary weakly coupled UV completion for supersymmetry breaking. We exchange particles spin 0 and spin. But there exists a whole part here of space of ulterior Gaussian, which is consistent with causality, that necessarily comes from eigenspins, exchanging the UV. And that's you note that eigenspin, in fact, infinitely many, because when I was doing the matching, I was writing Wilson coefficient equal some moments. There are also further constraints. There are some linear combination of Wilson coefficients, of moments, which don't return a Wilson, but return at 0. So it's a relation between the parameters, the couplings, and the masses of the UV completion. And this exchanging a spin 0 trivializes an infinite many of them. Exchanging L equal 1, which is equal to J squared equal 2, trivialize this one. But besides between these two, you need infinitely many spin and masses in order to satisfy those. And those populate all this part. This part here is nothing but a theory that lives here, plus adding on top an extra spin 1. The one that lives here is theory of high spin alone, adding a spin 0 in S channel. So the really interesting, you can say the non-trivial part is the one living here. And at the corner, we see, in fact, non-trivial theories, like non-trivial amplitudes. Okay, this one, for example, you see that for this one, you get infinitely many general spin at the same mass. Okay, some at the same m square, infinite tower of eigenspin exchange, which clearly cannot be coupled to gravity. I mean, not clear. I think you cannot couple it, so I'm not sure that it's there. I would say you cannot couple. So probably this point is not going to be completed with gravity, and this one as well. But here inside we find theories which are infinitely many spin, not at the same mass. And I'm not sure what kind of model of Susy breaking will produce that. But it probably must be a strongly coupled the model, it would be nice if it would be, for example, holographic breaking model where the deriva is not obvious in this picture. And so this was this parenthesis about Brastini, which is interesting on its own for a sort of if you wonder whether all models of breaking have been explored, this in a sense is the map. Any model of breaking has to produce a point within this design. So you can go and look at this point, this is the model that's produced it. And we have answers in this region here, but I'm not quite sure about this region. Of course, we can imagine that further constraints we haven't imposed. We'll shrink it further. Okay, let's go back to spin 3/2 after this parenthesis. So spin 3/2 alone was inconsistent. Now we fixed it, adding the only degree of freedom that could do the job was adding gravity. And moreover, you have to do a particular tuning and it will produce the unique theory of Brastini. So it's a nice lesson, I think. But this brings us to a new question. So we saw that gravity emerged from consistency conditions, but we know that gravity itself, when you're talking about the gravity, brings new consistency conditions, right? Like Swampler conjectures. So is there a new angle that we can take on Swampler? Are they connected, the constraints on causality? Okay? Is there a connection? So I'm going to show you that it seems there is a connection. I want to discuss this, for example. No global synthesis conjecture with gravity conjecture.
Brando,
Yes.
you argued that the real spin 3/2 kind of coupled to photon because it's real.
Mm-hmm.
But that's the minimal coupling. But you could have non-minimal.
No, in the case, well, so if it's the photon is massless, even in the low minimal cannot. If you make the photon massive, you can couple it, but effectively, and we check it doesn't change the story. And the reason is very simple because if it's if this massive photon you're adding is too heavy, basically you can integrate it out, and you are back to the contact tab we already excluded. If it's very light, you can go in the equivalence theorem, so you're basically adding a transverse photon that doesn't couple, and a scalar, which we checked also didn't work. So it's clear that it's not going to work.
Another magnetic moment that we do side.
No, that vanish for antisymmetry or opposite side real case. Yeah, if in the real case it doesn't. But that I'm going to add next. Look, is precisely what I'm going to add in the next slide. Give me 1 second. I'm going to add it, so you will see it. So I want to show whether there is a connection between causality and these conjunctions here. So I'm gonna do the charge case when I double my degree of freedom. I add a global U1. I double so now I have 2 line that I couple to form my Dirac mass. And this, of course, I mean the amplitudes are a lot of them because now I can organize my state as changing, sending particle with the same charge or opposite charge. Now when I do crossing, I can maybe flip the charge, but they have different helicities. So there's a lot of conditions and a lot of scatterings also. So actually it becomes problem kind of involved. So I spare you a little bit of detail. So alone, if you don't add anything else, it's not gonna basically you have theory. Yeah, basically you have twice the same bad theory is not gonna conspire become nice, so it's just still inconsistent. Now, interestingly, coupling this theory to graviton also is no longer going to be able to fix it. There are certain amplitude you fix it, other will still grow with e to the 4th. What you need to do.
What's the essential difference? I mean, why doesn't it work?
Well, if you think that was supersymmetry.
Oh, because it's just not going to be supersymmetric.
Well, exactly. So,
That's gonna happen.
I mean, of course, we know the answer beforehand. We have the model building that you expect that it's impossible, and this is confirmed by the analysis. So you look at the amplitude, you're able to fix some, which one? Those that for which the 3/2 was in the same multiple of the Garto, but not the other 3/2. was in another multiple, was a 3/2. Supersymmetry, I would say, is a 3/2 in the same multiple of a spin 1, not in the same multiple of the ground.
Or you could do any equals.
Exactly, that's where I'm going. N equal, precisely. That's where I'm going. Now you add N equal to indeed as a vector. Crucially, that's it. So I'm adding a vector with this monopole and the magnetic dipoles. And if without graviton, this one also doesn't work. So now, coming back to your question, I could have coupled it to this one, it's not going to work. I need to add both graviton and vector, then I find the solution. And the specific one. So I need to fix these dipole interactions to be gravitational in size. Here, which is expected. Because everything, if gravity has to play a role, everything else has to be gravitational in order to conspire for consistency to work. And moreover, the electric charge is also gravitation. That's interesting, because what are the lessons here? First of all, I cannot set the electric charge to 0. The global symmetry must be gauged. First lesson. So it seems indeed there is a connection from the causality constraints and the non-global symmetry.
The model was supersymmetric, the one that you decided on in this slide was. You're just looking at consistency. Did the final answer come out to be supersymmetric?
Yeah, this match exactly. At least one more. We check what I mean. Yeah, as I was saying, it's very preliminary. We did this calculation like 3 days ago.
Okay.
So, the one model of N equal to that we checked had precisely these couplings. So, in fact, this one is not only gravitation, it saturates the gravity conjunction. And this condition is precisely setting the magnetic geomagnetic factors to 2, okay, which is expected since the 70s, but it worked by Weinberg. Although Weinberg was doing stronger assumptions, okay, was assuming one subtracted dispersion relation, so as opposed to twice subtracted, so was imposing a better UV behavior than we have, and moreover, it was assuming that UV was weakly coupled, as we don't assume. It was also argued in this nice paper by Ferrara, Corrati, and Telegni in 1992, based on Lagrangian analysis in compton scattering, demanding that all factors 1/m in the propagator for the massive spectrum will cancel. And but was challenged. This paper and others were challenged by this paper by Deser, Pascal, and Borjo in 2000. They were arguing that there was some causality violation associated with this choice, G equal 2, for a spin, but then so another paper by Corrati Raman was debugging that argument. So back and forth, I think we see it imaginably clearly from amplitude analysis as a not easy. So there were proposals for this to be 1/J, this spin. And for the spin 1/2 is 2, okay? For the heavy spin will not be. And instead the G equal 2 seems the only choice. And indeed it matches the N equal 2. Yeah, I mean, this is the one example that we check it matches. Okay, so this brings me to conclusions. So the expectation, I think, is confirmed. So eigenspin isolation are inconsistent because of causality, and that's nice in a sense. It's good that our quantitative textbook don't start with a spin 5/2. It wouldn't make any sense. Being consistent here, so do not be a good start. So start with the low spin. You can make it consistent adding very particular, the two certain theories, specific theories are forced upon you because of causality, and you discover no theories, experimentality. And it seems there is a connection between causality and the small part conjectures. Of course, it didn't stress much. Okay, and I think it opens the space of model building for Susy-Blakey model. I think as we largely unexplored, it would be interesting to see how you populate the explicit construction, I mean, probably non-perturbative models of the breaking web, which point will populate in the space in the effective filter for the Gaussian. And given here at UCLA, I think I want to say perhaps be interesting to see whether these are an implication for the scattering of classical spinning bodies that some people here are interested in. Because it seems that one spin at a time doesn't seem a good strategy. And here it seems that there are constraints from causality enforced. So when you consider scattering of, I'm not sure, but it seems to suggest that when you scatter objects with very large spins, you should consider transition to other high spin channels which need a degenerative mass. And that's what you expect for a classical object. Right? A big object, the gap to the excited states is teeny tiny. Right?
You probably should talk.
Pardon?
You probably should talk.
Okay.
It resonates with recent people.
Okay. And another interesting thing, so we saw that the spin 3/2 plus graviton, we knew it was possible to fix this problem by adding gravity. And indeed, because of the argument confirmed that. But we don't know of any UV completion instead when you have a massive spin 2 and a massive graviton in isolation. Of course, we know when you have a Keck tower. But then all the other states are parametrically all at the same. The gap is always a multiple of the first gap. So it'd be interesting to ask, can I decouple, can I live like in a bigravity theory where I have just a massive graviton, a massive, say the first KK mode, and I push the rest of the tower very far, so or said differently. How crazy bicompatification can possibly consistently come up? That's I think is an interesting question. And that's all I wanted to say. Thank you.
Any question?
How long are you here for?
Just today, so I leave it tomorrow morning.
What time do you leave?
Tomorrow morning, or very early.
What's that?
Very early. Tomorrow morning, I'm leaving.
No, I'll bet you're here.
I hear tonight till we can go till 3 a.m.
All right, let's thank Brando again.